Hi everyone. Welcome back to Dave's Math channel. You can probably tell I'm back from vacation. I'm back in my studio. I got back earlier today from Utah. I had a really good trip. But anyway, I'm back home. So today I'm going to talk about one way to define the natural logarithm. This is in terms of an integral. Anyway, let's begin. So here's how we can define the natural logarithm. We could define it as this definite integral. The integral. So we say ln x is the integral from 1 to x of 1 over t dt. Sometimes people just write this as dt over t. And I don't know if you remember, but last time I talked about the power rule for integration. So this would be the power rule with the exponent n equals -1. But remember that case failed because in general the integral of dx over x to the n is x to the n plus 1 over what is it? No, x the integral of x to the n dx is the x to the n plus 1 over n plus 1. That fails if n is -1, because then you would get x to the 0 over 0. That doesn't make sense. That's undefined. So you have to use another method to define it. And you might as well define it to be equal to this integral. And let's just see what kind of properties it has if we do that. Well, geometrically, it's just by the definition of a definite integral, it's just the area under the hyperbola y equals 1 over x, or if you like, y equals 1 over t. And there's two cases you can look at. One case is where x is greater than 1. In that case, you get a positive value for the natural logarithm. It's just the area from 1 to x of under the curve y equals 1 over t. You can see that's positive. But if it's going to be negative, if t is less than 1, it turns out, I mean, I guess you have to prove this, that it's actually equal to minus ln x in the second case. If the limit is 1 over 1 over x. So anyway, that's how that works. And anyway, we still need to prove that. And another thing that's very easy to prove from this definition is ln1 is 0, because in this case it's just the definite integral from 1 to 1, so there's really no area in that case. Both of these cases shown. But how do we actually prove that with this definition, ln x is really a logarithm? We're calling it the natural logarithm. So it better be a logarithm, otherwise the name is wrong. So we'll really have to prove, I mean, it turns out this is sufficient to prove that it's a logarithm. We just have to prove that for all positive numbers x and y, we have ln of xy is ln of x plus ln of y. That's the definition of a logarithm. Logarithm of a product is the sum of the corresponding logarithms. So how do we prove that? Well, we just plug it in. Let's plug in the definition. So using the definition, ln xy is the integral from 1 to the product xy of dt over t. So we can split that up into two parts. You can always do this for integrals, by the way, because areas add. So we can write this as the integral from 1 to x of dt over t plus the integral from x to xy of the same thing, dt over t. Now we can use a trick called substitution. This is actually a very useful method for solving integrals. I'll go into this in more detail on a future video. But what you can always do to solve an integral, you can change your variables. So you can use what's called, you can substitute. So in this case, I'm going to change the variables. I'm going to use u equals t over x. And now we're thinking of x as a constant. Because as far as the second integral goes, it is a constant. Remember, this integral is over t. T has nothing to do with x, really. We're thinking of x as a constant. We're also thinking of y as a constant. So we can always define a new variable, u equals t over x. And if we do that, then we also have du. We have t equals x times u, and dt equals x du. And with that substitution, you'd get dt over t equals x du over xu, well, the x's cancel, so you get du over u. Well, that's nice because you're left with the same kind of integral as you had before. So now we can rewrite ln xy as the sum of the integral from 1 to x of dt over t plus the integral from 1 to y. The other thing I forgot to tell you is that you also have to change the limits of integration when you do this substitution. So since u is t over x, we have to divide both the integration limits by x. So the lower limit on u becomes 1, that's x over x, and the upper limit becomes y, that's xy over x. So now we have a second integral of a form 1, the integral from 1 to y of du over u. Well, by our definition of the natural logarithm, that's just ln y, and the first one's ln x. So we've just proven that the ln of xy is equal to ln x plus ln y. So we're done. We've proven that it is indeed a logarithm. That's nice. And since it's a logarithm, we still like to know what base it is. I mean, there is a number called e that's also Euler's constant, which turns out to be the base of natural logarithms. As a matter of fact, it used to be called the base of natural logarithms. I did another video, and I've actually done a few videos on e. It turns out to be approximately 2.71828. And it also turns out to be, I think, the second most important irrational number in mathematics after pi. So it's a very important number. And we can define E as just the unique number, the unique positive number such that ln E is equal to 1. In other words, the area, if I go back to the picture I showed a couple slides ago, the area, if we put the upper limit as E on the picture on the left, which is approximately 2.7, that area would be equal to 1. I think you can see there's a unique number, E, that does that. So, and now with that definition, let's give another proof that the derivative of e to the x is e to the x. That e to the x is its own derivative. How do we do that? Actually, this proof turns out to be a lot easier than the one that I gave you when I first defined the exponential function. That's why usually people start with the natural logarithm, and then they define the exponential function e to the x is just the inverse of that function. Well, let's first show that e to the x is indeed the inverse of ln x. That's easy. Because ln e to the x, since ln is a logarithm, that means that ln of e to any power is just that e to the x is just going to be x times the logarithm of e. Well, we already defined the logarithm of e to be 1, so that's just x. So anyway, so now how do we prove that the derivative of e to the x is e to the x? Well, that's easy. We're using sort of the inverse rule for derivatives. Remember, we can if we define y to be e to the x, then x is log y, and then that means dx dy is 1 over y, because the way we've defined the natural logarithm, its derivative is just 1 over x, if you like. The derivative of ln x is 1 over x, because the logarithm is defined the integral of 1 over x. So we have dx dy equals 1 over y. We can just flip things around. Dy dx is going to be 1 over y, if you like y, and y was defined to be e to the x. So we've just proven that e to the x is its own derivative. And that's, I think, a lot easier proof than I gave you last time. So anyway, that completes my video for today on natural logarithms. Thank you for watching. Long live math, and I'll see you guys next time.